Thank you, Shuj, for introducing me. And so, hi, everyone. Today, I'm very happy to be here to talk about my work on leakage resilient hardness with randomness. And this is a joint work with Professor Rafael Paz at Cornell Tech and Tel Aviv University. And so, today, the question we are focused on today is whether randomness helps in computation. So this is also referred to as the BPP versus P problem. This is arguably one of the most important problems in complexity theory. So in this problem, we ask, is BPP equal to P? And this is also called high-end derandomization. Or we can be less ambitious and just ask, can we derandomize BPP into determinist time t for some quasi-polynomial or sub-exponential function t? This is also called low-end derandomization. And as we all know, following the celebrated hardness with randomness paradigm, hardness of function implies derandomization of BPP. And this is a consequence of a beautiful line of amazing work starting by Bulu and Mikali and Yao, followed by Nielsen-Wienersen, by Fulton, Nielsen-Wienersen, Imperial-Wienersen, and Sardan, Trevis, and Madame. So for example, in the earlier work by Bulu and Mikali, they show that if discrete log is hard, then we can derandomize BPP in sub-exponential time. And Yao proved that the same thing holds if we assume a one-way permutation. So essentially, if you have a cryptography PRG, then you can derandomize BPP in sub-exponential time. And later, Impagliazzo and Wienersen showed that if we assume the complexity class E is not contained in infinite open size 2 to the power, well, say 0.01 n, then we can conclude that BPP equals P. And this result also extends to the low n setting. Well, we only need to assume X is not inside infinite open P/poly. Okay, amazing results. However, is this result tight? So is the result we get from hardness with randomness paradigm tight? Unfortunately, as we might know, despite of years of research, well, decades of research, there is still like a seemingly huge gap between what is sufficient and known to imply derandomization and what is necessary and known to imply by derandomization. And let us ignore, well, infinite open issue, difference between like a high-end and low-end derandomization. To derive derandomization, we need hardness for uniform classes, but from derandomization, we can only rule out easiness for non-deterministic classes. So our central question today is, well, can we close this gap? And let me mention that there are some recent improvements over, well, the necessary condition, but there's still like a gap here. And our main theorem today says that, yes, we can get a sufficient and necessary condition. So we show that leakage resilient hardness characterizes derandomization. And the formal statement would be there exists some constant C. Well, think of C as being 3, such that BPP equals P if and only if there exists a polytime computable function f that is almost all input leakage resilient hard with respect to n to the C time attackers and n to square root and bit leakage. Well, as we shall see very soon, leakage resilient hardness is really a classic notion and was studied in the 80s. And well, there's like a subfield of cryptography called leakage resilient cryptography that studies this notion. So before I introduce the notion of hardness, let me put some remarks here. So first, this gives a categorization. So our assumption here is both sufficient and necessary. And it also extends to the low-end setting. It also extends to characterizing derandomization of MA and also average case derandomization. And lastly, our results kind of morally explains by how much does IW overshoots the problem of derandomizing PPP. So as promised, let us introduce the notion of leakage resilient hardness. So here we'll focus on the factoring function. And we let x equals p times q for two large primes p and q. And we define f of x be the factorization of x. And under the famous factoring conjecture, we believe that, well, this function, factoring, is hard to compute for polynomial time machines. But what if you get, well, some leakage from f of x? Well, there is a trivial algorithm factoring f of x, computing f of x with n over 2 bits leakage. Well, we just ask for p or q, whichever is smaller. And Revitz and Shamir in 5 show that, well, we can do this with only n over 3 bits of leakage. And later, Cooper-Smith 97 shows that, well, actually n over 4 bits leakage suffices. And later, Maurer in 1986 showed that there is a heuristic that works with epsilon times n bit leakage. So the question here is, well, can we do better? Or is this function leakage resilient hard? So let us introduce our hardness notion formally. So there are 2 parameters that are important here. The first one is a capital T. It's like a runtime bound. So we are considering attackers that runs in time t. And there's also like a length parameter L. So the attacker is allowed to take at most L bits of leakage. So our definition would be, we say that F is TL leakage resilient hard if no probabilistic T-time attacker A can compute F of X even with, well, any leakage, such that first, the leakage is at most L bits, and second, it is like T-time computable. However, let me note here that it is easy to show the existence of a TL leakage resilient hard function. Well, just take the random function. We will also need some explicitness requirements. So basically, we require like this function f should be computable, say, in polynomial of t. And let me mention that here we also require almost all input hardness. Well, you have seen this in the previous talk and following Chen et al. 21. So in this hardness, we recall that the hardness condition holds for almost all input x. So for any attacker A and like any efficient leakage, they can only succeed on computing f of x for like finitely many x. So here's like a sequence of input, and there's like some x, such that after this x, like any input that's larger than x, you will fail on that input x. So this is a hardness notion that we need. And now we are ready to give the formal statements of our results. So we rely on the notion of nice classes. So we say that C is a nice class of running time bounds. Well, if it's basically closed under polynomial composition, so we recall that for any t, if t is inside C, then p times t of q is also inside C. Then our statement is that there exists a constant C such that for every nice class of running time bounds, for any epsilon that's between 0 and 1, the following are equivalent. So first, BPP is in D times C. And second, there exists a C-time computable function that is almost all inputs leakage resilient hard with respect to n to the C-time attacker and n to the epsilon bits leakage. And then we immediately have the following 2 corollaries. First, if we take the class C to be the class of polynomial functions, then we get BPP equals P if and only if there exists a polynomial time computable F. And we can also take C to be, say, the class of sub-exponential function. And then we get BPP is inside sub-exponential time if and only if there exists a sub-exponential time computable function F. And as mentioned before, our result also extends to characterize the derandomization of MA. So here we consider a relation R that is computable in non-deterministic time C, and it also almost all inputs leakage resilient hard. And we show that this is equivalent to MA being derandomized into non-deterministic time C. And this result also generalizes to the low-end setting. And also, our results also extends to the so-called effective or average case derandomization. So in effective derandomization, we no longer ask our derandomizer to, well, succeed on every input. Rather, we only ask, well, no PPT machine can find an input on which our derandomizer fails, except with negligible probability. So to characterize effective derandomization, we only need a polytime computable function f that is leakage resilient hard well, with respect to any sampleable distributions rather than almost all inputs. So this is, well, in some sense, a cryptographic derandomization because, well, no efficient machine can find inputs on which it fails. So let us mention some related work. Chen et al. 21, as you might heard about, they showed that almost all input hardness of shallow functions with 13 efficiency requirements implies BPP equals P. And they also get a partial converse. So almost all input hardness is necessary, but without the channelless requirements. However, we do get a if and only if. And a recent work by Liu and Pass in 22 showed how to characterize the randomization using Kolmogorov complexity. And they showed that BPP equals P if and only if for all auxiliary input sequences Z, the conditional level Kolmogorov complexity problem is hard with respect to Z. So, however, they require, well, like hardness of a family of problems because this has to hold for like all auxiliary input sequence, and it doesn't generalize to the low end region. So let us move on to, well, look at our proof. So today we're going to show equivalence between BPP equals P and almost all input leakage resilient hardness. And let me remark here that our proof is mostly conceptual, and we will focus on the high-end region, namely BPP equals P. So let us look at the proof for theorem 1, which we aim to show that if there's a leakage resilient hard function, then BPP equals P. And to show that BPP equals P, it is enough to construct a so-called targeted PRG. Well, we also heard about this before, but let me introduce this notion again. So a targeted PRG is an efficiently computable function f that takes a target string of length n together with a seed of length c log n as input, and it outputs a pseudo-random string. And we ask it to satisfy the so-called targeted pseudo-randomness property. So for any target string x, the targeted PRG G on input x with a uniform random seed. So the output distribution should be indistinguishable from uniform distribution in the eyes of any linear time Turing machine that also gets the target string as input. And we ask this holds for all sufficiently large x. And as showed by Golak 11, targeted PRG implies BPP equals P. Well, you can just think of replacing the random tape with a pseudo-random string. So now it suffices to construct a targeted PRG, and let us mention the high-level ideas behind our construction. So, well, given a target string x, we will use this target string and the leakage resilient hard function f to get f of x, and we interpret, well, f of x as the truth table of a hard function, and we'll use it in the NWSTV PRG or the so-called black box PRG construction. However, the issue here is, well, Nielsen-Williamson reconstruction procedure requires non-uniform bits, but here f is only hard with respect to uniform attackers. And our solution here is to notice that Nielsen-Williamson PRG is still secure if the truth table G is hard to print with short and efficient leakage of truth table of G. And such hardness condition will be guaranteed by our almost all input leakage resilient hardness. And let us proceed to our construction. So the targeted PRG here is just Nielsen-Williamson PRG when instantiated with the error-correct code of f of x, where f is the leakage resilient hard function and x is our target string. So to show that this is a target PRG, we assume for contradiction that there exists a distinguisher D such that on target x, D of x breaks our construction. And our goal here is to construct, well, like an attacker A and a leakage function leak, such as A on input leakage will compute f of x, and this is going to be a contradiction. So our leakage function is constructed as follows. So it takes like the target string or like the input x as inputs, and it also takes another input z, which is supposed to tell you what f of x is. And it will construct the PRG because, well, it knows f of x, so it can compute, well, arrow-crediting code and compute Nielsen-Williamson, and it will interact with the distinguisher d to obtain the n to the epsilon bits on the truth table of G that we need in the Nielsen-Williamson reconstruction algorithm, and also some auxiliary information in arrow-crediting code. And then it will just output those Nielsen-Williamson auxiliary bits. And our attacker A inputs the X together with the leakage. We'll first use the leakage bits and together with the distinguisher in the Nielsen-Williamson reconstruction algorithm to get an approximation of our code word. And we will finally invoke the list decoding algorithm, and we get f of x. So like the attacker A together with the leakage will compute f of x. This contradicts to the leakage resilient hardness of f, and we conclude that our target PRG is indeed a PRG, and therefore this concludes our proof. So let us look at the proof for the other direction, in which we assume BPP equals P, and we want to show that there exists a leakage resilient hard function. So let me give the proof outline of the other direction here. So our proof proceeds in 2 steps. In step 1, we show that, well, if you take a random function, it's going to be almost all input leakage resilient hard. And in step 2, we're following the ideas in GoLAC 11, and we show that we can efficiently de-randomize this random function on every input x, assuming that BPP equals P. Of course, this proof outline is a bit oversimplified, and we refer you to the full paper for the actual proof. So let's wrap up. Today, we have seen that leakage resilient hardness characterizes de-randomization, or more formally, there's like a constant C, such that for every epsilon, the following are equivalent. First, BPP equals P, and second, there exists an efficiently computable function that is almost all input leakage resilient hard. All right, so let me take the last 5 minutes to take a step back and look at our hardness with randomness paradigm. So as mentioned before, so in the above, we have the conditions that are sufficient, and in the below, we have the conditions that are necessary. And as we just seen, like the leakage resilient hardness assumption is both necessary and efficient, so it's going to be a line in the middle. So we can ask, well, how big is this gap? All right, so how big is this this IW assumption, is this gap between IW assumption to and a sufficient and necessary condition? Or alternatively, by how much does the IW assumption overshoot the problem? So let us recall the IW assumption. So it assumes that the complexity class E is not inside infinite orphan size 2 to the power of 0.01 n. Or like alternatively, we can find, well, like an exponential time computable Boolean function G that's on input length n, outputs like 1 bit, and it is not computable by circuits of nearly exponential size. So given G, well, let's massage it a bit, and we will get like a polynomial time computable multi-output function f. So what is this f? So given some like input to x, input to f, x of length n, we let m to be the logarithm of n. And here f of x is just defined to be, well, gm of 1, gm of 2, all the way to gm of n. So here f is essentially outputting the truth table of G. So because, well, like we are outputting the truth table on inputs of only logarithmic size, so therefore it is going to be like a polynomial time computable, and note that this is like a multi-output function. So there, let us make a few observations here. So first, like this function f is constant over every input size, because we're essentially print the truth table, so well, on the same inputs, you print the same truth table. And second, f is actually almost all inputs leakage resilient hard, even with respect to unbounded time or even non-uniform leakage. Well, because it has like it is hard against circuits. So if we consider functions that are not constant on every input length, and function that is almost all input leakage resilient hard with just efficiently computable leakage, then we can get a condition that is both necessary and sufficient for derandomization. So this concludes my talk, and thank you for listening.
In the proof, can you explain a little bit why the leakage is efficient?
Yeah, so this is a good question. So if you consider like Nielsen-Wilson reconstruction algorithm, so it kind of proceeds in, well, first you have like you assume like a distinguisher that breaks the PRG. So you distinguish like uniform from random, and you do this like hybrid arguments where you find like on which like position the distinguisher wins like with enough probability. And remember, like each output bit of the Nielsen-Wilson PRG is just, say, like the evaluation of the hard function on some bits. And therefore, like to kind of to use this like then after this hybrid argument, we can have like a distinguisher that's, well, by using like Yau's like indistinguishability versus unpredictability, distinguisher will predict, say, like the ith bits of the generator. And to use this distinguisher, the advice you need is basically, well, because it's a hybrid argument, so like everything in front of you, ahead of you is just like evaluation of the hard function, and every other thing like after the position I is just like uniform random bits. So to use the distinguisher, you just need like evaluation of the hard function. So if you get like, say, the truth table of the hard function as like inputs, then you can just compute the error correct codes yourself, and you compute like those like value you need from the error correcting codes. So.
You need to also leak the I itself.
Yeah, but I itself is actually like efficient computable because like cause there's like say like n choices of I, and like one of them is going to be good, so you just like sample it. Yeah. Yeah, I guess we have heard about like this in like Nicolas' talk, and yeah. So I guess like our results like only extends to MA, but for like characterizing AM, like you need like a bit like extra work here, like there, because it's actually like I guess like the if I remember correctly, like the problem is like in the converse direction where you want to show like if like derandomization of AM implies like some hardness, and there because like you cannot like flip, in some sense you cannot like diagonalize, this diagonalizing argument won't work because you can't like flip the results. So like you don't get like characterization. And I think for something like, if you want, I think, yeah, I will refer you to like Nicolas' paper for like more details on this. Yeah. Yes.
So if I remember correctly, but where you were oversimplifying at the end on the IW 98 was I-97 assumption, is it
Oh,
you allow the algorithm A in your leakage resilient to kind of run in time bigger than n, and so it's not quite quite immediate that the IW assumption. It's not obvious that the IW assumption implies the leakage resilient, or it's kind of indirect to get that. I'm wondering, is there a variant of your assumption where?
Yes, yes, of course. Like yes, you need to. Yeah, like behind what I'm hiding, you need to consider like a kind of a version of local hardness. It's like given the leakage, it's hard to print like each bits of the function, and this allows you to consider, well, like a sublinear time hardness of like leakage resilient hardness. Yeah, there's like a bit work to do there, but if you pick the right notion, it will become immediate that IW implies leakage resilience.
I see, and that other notion is equivalent also to like Thomas BPP.
Yes.
Great, thanks.
Yeah, that's a good question.